time. So, สวัสดีครับ Good evening and Selamat malam. Nama saya Panit. My name is Panit. I'm the Vice Chairperson for the Technical Program. And welcome to SPE Thailand Technical Meeting. So I'm very happy again to see everyone face to face tonight. And hopefully we can continue this journey for the next month, even though the situation now is getting a little bit challenging. So under this condition, we still keep you informed of our mission, which is what's going on in our industry, and would like to have the knowledge available to you through our monthly technical meeting. And tonight, very special night, we have our guest from Indonesia. We have Pak Riko Mudayana, our technical advisor from Expro. So today he gonna share us the story of fiber optic sensing, closing the gap for diagnostic and monitoring in well intervention with us. And again, our vision is to be open for sharing information with our peers and across company, so we can provide energy for our kingdom, and of course meet many new faces, and would like to see the smile on your face. Smile. So agenda for today, the usual, we start with the section announcement. Continue with the talk, and then closing remark and lucky draw. Okay, let's start with the numbers before you fall asleep. So for the membership, we have 594. We got 272 from the student members from 4 chapters: Chulalongkorn, Suranari, Prinop Songkhla, Chiang Mai. And not only to retain, we also have new membership as well, around 40. And you can look at the trend here. We got shoot up in June, which is a good sign, similar to oil price. So hopefully we continue the momentum of the membership here. And of course, please invite your colleague to join SPE, as we are the largest professional oil and gas industry, where you can regularly meet in this relaxing environment. And please also remind your friend or yourself if you haven't renewed your membership. I'm not going to go through the SPE membership benefit. I believe you see them every month. But again, just to emphasize that we are one of the most active section in Southeast Asia, where we have regular activities that you could participate. And this is the most important slide. This is our sponsor that make our event happen today. So may I have a loud applause to our sponsor. So if you want to see your company logo over here, please contact any of the board member. Board member, can you raise your hand? Okay. So you can reach any of us and then have your logo here. Do we have any student tonight? No. Okay. Thank you very much, and give them a loud applause. They are our future. Thanks for staying in oil and gas. Not going anywhere else. Professor too. Yep. Professor too. All right. Without further ado, let me hand the stage to Kun Kasian, Program Chair, my boss, to introduce the speaker for tonight. Thank you. Terima kasih.
Terima kasih Pak Panit. Good evening, Kap. My name is Kasian. I'm the program chair for SPE Thailand. Let me go straight to introducing, so I'm not going to waste your time. So our speaker tonight, he's currently the technical advisor for well integration product lines with Expro Asia region, based in Indonesia. Prior to his current assignment, he spent over 30 years with Sukhumvit, where he started his career as open-hole electric line field engineer in Indonesia, and later on moved to UK and Norway, operating mainly in rigless well interventions. After 12 years in the field, Riko moved to Indonesia again, assuming the position of Field Service Manager or FSM, and subsequently Customer Support Manager. He was then assigned to Oman as Account Manager and later on being assigned as Domain Champion for perforations, well integrity, production locking, case hole formation evaluations, and conveyance systems. He maintained his positions of Production Service Domain Champion until he retired from Schlumberger in 2020, 2 years ago. Mr. Riko graduated from Institute of Technology Bandung with an electrical engineering degree. Ladies and gentlemen, please a warm welcome to our speaker this evening, Mr. Riko.
Thank you, Mr. Kasian and Panit. So it has been an honor for me to be given a chance to present this technology. And this technology actually is not quite new because I just talked to Rob that he's been like running this fiber optic for many years back, and but there is something different that I would like to present why this time now is different. Because when we have this technology, actually something that I would say is quite revolutionary in terms of the logging acquisition. But this technology been underutilized. Why it's underutilized? Because one is that a couple of things actually. One, the deployment is not easy and it's quite expensive for many of the company. So the second one is that the ecosystem or the environment is still not there. So basically, currently we have a system where we can deploy easily, which is I would like to talk for the next 30 to 45 minutes, and then also the way we work now is changed quite different, where we focus on how to address the thing more cost effective and more efficiently. So we have something different that, or it's not something different, something that match with the current demand, where we need something that we able to use for the diagnostics or monitoring in order how we can get the whole of our works in our well intervention as cost effective and efficient. For that, I would like, this is a summary that or outline that I would like to present it today. One is the background, which is why this technology give you a better chance to be utilized today and what the challenge that we can address with this technology. And the second one is go a little bit more on the technically of how this thing works, which is the principal operation. And after that, I would like to talk about the two different applications. One is for the well integrity application, which is one of the biggest challenge in well intervention. And the second one is more on the well performance application before I closing with a summary of this fiber optic sensing. Now the background, maybe many of you know this picture, right? Even I never been there, I always thinking this is one of the picture that always what I would say is like make me interested to actually to go there. So this one is the Niagara Falls, where years by years is always flowing, right? So this is where when we talk about this one, it's like a recycle by itself, right? So it's always the water always there, and we always be able to enjoy this one. And when we look at where we work, we hope that we have this situation, but unfortunately not, because when we talk about the oil and gas, production, we never have the similar as what we see on the Niagara Falls. Why? Number one is that the oil and gas is limited. The number is limited and there is no recycle. Number two, when we talk about the oil and gas production, by natural, it's always decline. And the third one, as you experience by the time, the longer you have your field, the more difficult to produce or the more expensive to produce at the same time. And the last one, the longer you operate your field, the more potential you encounter problem. So because of that situation, what we have now, if you're dealing with the field that you already operate for many years, is that the chance you can get more oil is more difficult, while the cost to produce it is more expensive. So this is a situation where the industry finally react on what to do on this situation, because at the end, what we have to have with our field is how to produce economically. But before I talking about what the industry react, I would like to talk about where we are actually on the life of the well, from the beginning of the exploration until when we abandon the well, right? Many of SPE members, actually, if I can divide, we can divide into two parts of the phase of the life of the well. One is when we more focus on the study and evaluation, which is probably, I'm not sure why with the audience here, but look like many of them actually involve a lot on both sides. Whether you are focused on the study and evaluation or on the second phase of the life of the well, we are focused more on the innovation and the practical approach to produce the well more efficiently. So from the study and evaluation, this is where the decision is being made, whether from the exploration you have economic enough reserve to develop, or you have to decide something different. And then when you decide to produce the wells, or when you do the characterization of the study and evaluation, the product is the reservoir characterization, where this is it's like a blueprint for you for the rest of the life of your well. How you're going to produce, how much you expecting you can produce from your field, and so on. While on the other side, after the production, what you have to focus on is to maintain or to ensure that the well still being able to be produced economically, number one. Number two, you try to get as much as oil or gas recover from your reservoir, which is try to get as much as your recovery factor. What we need on this one is, number one is that your reservoir characterization has to be accurate. Number two, you have to maintain your well integrity, because two things to produce. One is you have oil on your reservoir. Second one, you have to have a good well integrity in order to produce it. The question now is whether this is always what happened. Of course not. Why? Number one is that sometimes, even though you already spend so much time, so much effort on reservoir characterization, when you come to the production, sometimes they're not always the same as your initial study. So you have an uncertainty on predicting the performance of your field. And the second one is one of the biggest challenges that we have is this number. Anybody can guess what this number are? So in UK, they mention about 47% of their live well have issue with the well integrity. Which means what? Which means that when you have this issue with the well integrity, you will have issue with the how to produce optimally. or maybe you cannot produce at all if the issue is too big to be handled. The other one, which is more or less the same study or the same record they have in US, in the Gulf of Mexico, about 45% of the live well have issue with the sustained casing pressure. Some of them you can get away and you can keep producing. Some of them you probably have to stop the production. So what you have to do is that two things. One is you have to make sure that you don't have uncertainty on your reservoir. The second one, you have to address this one, the well integrity issue, in order to get your well producing remain economically, and you can get maximize your reservoir recovery. Now, how the industry react actually, or more actually, is how the industry try to address this well integrity issue. When we talk about this one, there is always two things, right? One is, the first question is what the problem is. The second one is how we going to address or to handle this problem. And because we have this pressure on the gain getting less while cost getting high, what we can do actually is try to manage the cost as effective as possible. Do we have that? Yes, of course. The industry is reacting very well on addressing the problem of the well integrity by several measures. Number one is they are going smaller. Maybe when Ron or Rob start with the oil company, the way they have to do with the addressing the well intricacy problem is always move the rig to the intervention. Later on, they develop a more cost-effective way to do it using the coil tubing. And today, we have what we call a coil hose, which is less, in terms of the size, it's much smaller. And in terms of the mobilization and the people involved on the operation, also smaller, which is bring us to the cost-effective operation. But of course, by doing smaller size, we have a limitation, right? So it's not all the problem we can address. Before, when probably Ron still young, whenever he bring the rig to the field, he said, I can handle any problem, no matter what it is, right? But with the coil tubing, maybe it's different. With coil hose, even less capability. But you need to know exactly what the problem you're going to have, right? The second one is the going smaller. You know, when in the past, when we have a small platform, we want to do intervention, what we have to do, we bring the parts, we bring the rig to do the intervention, because why? The platform simply does not be able to accommodate the equipment for the well intervention. To address that one, the industry go with the smaller and modular unit, which is now you can put different equipment as what we needed, and then just utilize the space in the platform. The next one is we develop a technology where it is fit for purpose, which means if you have issue with the shallow depth problem, you don't need to have the equipment that can handle the high pressure deep well, right? So this, by selecting the right fit for purpose technology, you can save a lot of your resources, a lot of your costs in order to address the problem. And last but not least, you also start developing a more efficient system in handling, like what you call it, subsea wells, well without the rig, using the riserless intervention. So instead of going with the big rig, you can go with the probably like smaller ship or bars to do the intervention. So all of this, of course, there is a cost to use it. what the cause. You cannot handle any condition. You have to know exactly what your problem is before you decide using this technology. So this one come up to the question, what the problem is. Because if you know the problem, you know that the problem cannot be handled by whatever option cost effective, then you will not mobilize that equipment. So the question on the what one, actually when we're talking about the well integrity, actually it's quite challenging. First we have to accurately identify what the problem is, right? But to identify is not easy. Why? When we talk about the well integrity problem, we're talking about problem that may appear from the wellhead to TD. So can be anywhere in the well, right? So if you have been like familiar with the logging, to log from surface to TD is not easy, right? That's one, and very costly. The second one, what you face is sometimes it's not like single problem. You probably see, oh, I see a problem on my joint here, but there might be another problem somewhere else, or the worst, you're probably dealing with the problem from different strings. So it could be on the tubing, could be on the casing, production casing, could be on the 1338 casing, and so on. So you need to know exactly where the problems, how many problems, before you mobilize the cost-effective mean of addressing your problem. The next one, this is probably if you dealing with the problem with the leak. Most of the leak is like weak and intermittent. What that means, if in the past or during my time, if we have this kind of issue, it's very difficult to identify what is actually the problem. Why? Because it is intermittent. We probably, when we try to find on the bottom of the wells, and actually the problem is at the surface, by the time we reach at surface, the problem on the indication is no longer there. Which means what? We probably have to wait another day, another time, just to see section by section where actually the problem is. And also, this is probably is not seen as a problem, but actually has a big potential problem. What we call it is a hidden potential, hidden problem. Hidden problem is such as what? Such as if you have a high pressure gas, for example, with the nearby shallow sand, for example, if you have leak, you will probably have a cross flow and charging the shallow sand with a high pressure gas from the reservoir. Initially, you did not see that as a problem, but when you drill a new well, or when you try to produce from somewhere near surface, you suddenly have a high pressure zone from that one. So this kind of problem is the one that you have to identify before you decide that I am going to mobilize my cost-effective mean to address it. Or if you know it's not be able to handle with the equipment that you have, then you probably go with the old list. You have to mobilize the rig, you have to provide with the super duper ways of addressing your well problem. Now, how we come up with the correct answer on understanding what the problem is. So we need a capability to diagnose. Maybe many of you have been when you kid, or maybe no, right? Never change when you see the doctor because you're sick, for example. What you tell the doctor is, one is what your symptom. So what the doctor do to you after you telling the symptoms. That never ever change is that the doctor is always use two things, right? At least. Number one is use the stethoscope to listen, and use the temperature, use the thermometer to measure your body temperature. From that, then the doctor can come up with their diagnostic, whether you need prescription to address your body problem, or he will recommend you for further evaluation. If you think that you probably has a more serious problem, then you can address with the listen and measure, or you will probably being taken action immediately because the doctor see that you need that immediate action on you, or you probably, if you want to go on the other big operation, it can be a way of understanding whether you're ready to do the treatment or not. And the last one, probably you are okay, you are healthy. It's just simply to monitor your condition time by time, so when something goes wrong with your body, at least you know as early as possible. Now, this is your body. What about the wells? When we talk about the well, what we normally have is a slick line. Of course, until today, we all know what the slick line capable of, right? We know they are very useful in many of our operation, and in most cases they are always there on the beginning. But what the lack of the slick line is, it's only limited to almost like mechanical work. Now, can we expand the capability of slick line? The answer is yes. By what? By giving the slick line capability to listen and to measure, just like our doctor do to us. How are we doing it? This is what we call the fiber optic sensing is. So what we do with the slick line, when you talk about slick line, normally the slick line is made by a solid steel wire. We can make the same wire, but it has hollow inside, and we put the fiber optic in it, right? So with this one, now we can deploy the fiber optic in any wells where the slick line can. So these are the things that I mentioned early on. Before, to get the fiber optics in your well is not easy. Why? Because in the beginning, what we do with this fiber optic is we always put the permanent installation. If you're not having on the beginning, then that's it. You don't have it. Now, if you have it, if you don't have it, and you see there is an application for it, you can just call the slick line and they can do it. Now, what we do with the fiber optic and the slick line is two things, right? One is what we call it the distributed acoustic sensing. The second one is the distributed temperature sensing, which is like I mentioned earlier, where the doctor need to listen and to measure your body. Now, with the slick line, you also can do listening and measuring your wells, the whole wells, not only one part, but the whole wells. So with this capability, if you have slick line with the fiber optic sensing, then you can utilize the slick line to get the prescription of your well problem, or to know whether you need further evaluation, or to know whether you are ready for the heavy intervention, or you probably simply just want to monitor your wells, how the performance today, and when we have the next 6 months or the next 1 year, whether you see something that you can do about it to improve your production or not by continuous monitoring of this one. Now I like to talk about the principal operation. Okay, before I talk about this one, I like to mention a little bit about the technique of logging. Probably every one of you are familiar. When we log wells, the case hole, open hole, what we do is that we lower down the tool with the sensor on the tool to the target that where we want to evaluate or to measure, and then we move the cable along with the tool and the sensor at the same time and record whatever data we try to get. So that one, we need time, and the sensor agrees only in particular tool. The fiber optic, when I mentioned it's quite revolutionized, is that the whole cable or the whole fiber optics actually we turn into sensor. So what see here is from the surface down to the bottom of the well, this fiber optics work as a sensor. The beauty about this technology is that when you talk about sensor, what you need is you need electronic and you need power. Two things that normally can easily fail, right? Fiber optic sensing, you don't need that one donor. You just send the sensor, which is your fiber optics, and there is no power, there is no electronic. Everything that we need as power and electronic is at surface. So we have two panels where one is specific for temperature sensing. The second one is specific for acoustic sensing. The question now is that if you have the whole length of fiber optic, how we differentiate between the response on the bottom, the response on the middle, and the response at surface, right? So this is why this fiber optic is very useful. The way it works is like this. It sends a pulse of light, and while this pulse of light traveling, it refracted back a light to surface. This is where we try to record this data. So the refracted flight or the backscatter flight carries some information for different depth of the well. So this is one of the advantages using the fiber optic. You turn the whole cable or the whole fiber optic as your sensor, and you collect that information while the pulse is moving down. Can you guess how fast this recording happened? So the speed of light, you get the data from the wellhead to bottom in the like this. While you log, what you need to do is you start power up, you're logging slowly, and it's really like you see on the case, so it could be like 1 day just to get the whole data recorded. This one, if you're not happy with the one recording, you repeat, you repeat, you repeat, you repeat. So you have pile of data with the information. Anything happen in the well, you will capture it, you record it, and later on you can use for analysis. How this distributed temperature sensing work? Sorry, this one is you cannot see the light. So basically, I just go through it. The refracted light, actually, we should thanks to 3 gentlemen who look at this one. For me, maybe I never thinking, but that 3 gentlemen think about the refracted light. There is a Raman's look, and there is a Relay's look, and I cannot read. Another peak in here. So what this one work is that when this refracted light back to surface, there is a 2 peak here, which is called Raman stock and anti-stock. This is the anti-stock, this is the stock. This one is sensitive to the temperature where the refracted light coming from. And by look at this one, or look at the ratio between this and this, we can convert that to the temperature of the well. So it's very easy. You just one flight and you get. Now, how accurate? How accurate is depending on how many data that you recorded and averaging. So basically, you record 5 minutes, get the average, it will go more accurate than if you say only record for 1 minute and then averaging. So this is accuracy versus the time that you record. For example, if you have a, this, the way we measure, there are two different techniques. One is using a double fiber optic, which we send one side and the other side, or we can use also single one. Single one means that you just send transit one and then let it go. There is a slight difference, but not much. In many applications, actually one is enough. And the way we improve the accuracy of the resolution, we just how many data you recorded and average for that purpose, right? So if you 10 minutes, for example, with this double-ended one, and this one is for the 4 kilometer, which is average well probably less than this one. You can get the accuracy of 0.1 degrees Celsius, which is good enough for many of the application. So this is the actual data that we get from the real measurement of the well. What we normally do is you send the data at you measure the data at one point, and you get in less than a second, you get the whole measurement of the well, and you repeat first time here. And what we do normally, we change the well condition depending on what the objective is. From there, we will know the changing when the condition of the well is being changed. So that's how we come up with analysis of depending on our objective, right? So I'm not going to the detail on this one yet. I just want to show you how we look at the data. So here is what we call it the absolute. When blue is for low temperature, red for high temp. So basically it's a low temp and then going to high temp. And in most cases, if you look this one, you may not see anything. But when you look at the relative difference, so basically you pick up one of the line as your reference and compare to that reference, and you will see something featured here. You see here like heating up. This is a blue is like cooling off. This is another cooling off, and this is another heating up, and so on. So basically, we use this kind of different way of look at the data to get a conclusion on what we are looking for. We also, many of us, like myself, because I used to with the logging data single curve, I rather like also to see how the single curve look like. So we can also extract at any depth how the response of the single curve look like, and then you can compare to other measurement of the logging data. For example, if you want to compare with the PLT, or you will compare to the caliper, multi-caliper reading, and so on. That's the distributed temperature sensing. Now, what the second one? The second one is what we call it the distributed acoustic sensing, which is equal to listening for the doctor. The way it works is similar. You send a pulse of light down to your fiber optic, the refracted light you record at surface, and your interest is on the relay peak. What we're looking at is the coherence between your original signal to the what you receive back. So what the coherence means that whenever you have a vibration or noise at the depth where you have this reflection, it will give high coherence, not high, but the shifted on their peak. It's not coherence. So this one, by this one, you will get the whole picture of your wells in terms of the noise. Why this one important? Because, for example, like if you want to know whether there is a leak or not, when there is a leak, what we will see? One, on the temperature, you must have a deflection, right? But everybody knows well never have like straight line. It's always changing because of different formation, different heat conductivity of the well, and so on. So we need to confirm that one with the noise. Why? Because whenever there is a leak, which is in case of addressing the well integrity problem, we want to see the temperature change and we want to see the noise and that particular depth. So this one will be the key for the measurement. So now what is the challenge here? If you talk about maybe 10, 20 years ago when people start looking at this data, the amount of data that we record is quite huge, like terabyte. I don't know, I never have a terabyte. Gigabyte is already giving problem on my handphone, right? Terabyte, it is 1,000 of a giga. And I don't know, maybe Rob can share that when you have this big data, normally people just put it somewhere on the cabinet. Nobody really look at it because this is too big to handle. Current development on this data handling allow us to have this data being handled in the field, and then within 6 hours we get something that we can interpret. How it works? So basically from the giga or terabyte of data that we record from the wells, this is probably like one day we have about 2.5 to 3 terabytes. We just pick up the one that is meaningful for our evaluation into somewhere like a gigabyte, which is in many cases we could send it to the interpretation center. Or if that one is not possible, we could also generate the picture type of file, which is only megabyte, just like the internet type of picture. So we have two options here: either you dealing with the gigabyte data, less than 1 gigabyte, or you dealing with the megabyte of data where we get the XML picture. So how we get the one? So basically when we talk about noise, what we record is for this one is a capable record up to 10 kilohertz, right? And there are some ways of looking at different frequency for the interpretation. For example here, the same data, when you look at from 0 to 5 hertz, so basically this one is from top to bottom, this is a time, and the blue one is when quiet, the red one when it is noisy. So what we see here in the surface, you have like a lot of noise and then less noise and then quiet here, but you start seeing something here and another noise here, another somewhere here, and another noise here. And when we look at on different frequency, initially you do not see this one, but you start picking up something here, and on the higher frequency again you see different picture. So this looking at the data in different frequency gives you the opportunity or the capability to evaluate what happened in the well. And maybe anybody who has involved on the analysis or on the evaluation, especially of the problem, you never rely on one measurement, right? So what we normally use for this particular application, we try to gather as many as information as possible and put them all together. Like for example, this one, we have acoustic sensing, we have a temperature sensing with different way of look at it, as I mentioned before. You also need to know what the compilation diagram is. You probably want to add some of the open hole data or single curve measurement and then layers of your wells in terms of the formation. So all these things give you the information that when you put together, then suddenly what you see on the response make sense and you come up with the with the conclusion. So this is one of the things that we recommend or we try to implement whenever you're dealing with this one. Don't rely only on one measurement or two measurement. Get as many as possible the data, and then you start try to read it or try to evaluate or try to analyze. Now I want to go on the well integrity application, which is, as I mentioned early on, this is one of the area where it's become like quite a big challenge for the well intervention, which ultimately gives you a economic life of your well extended, or you get more recovery from your reservoir or from your well. So this talking about the wells where, you know, when they design early on, they already plan at one point you may need to have lifting, artificial lifting. So for this well, has been prepared to have a gas lift at later stages of the production. So this well has been producing like 2,000 barrels per day. And what happened then is that suddenly they have a pressure on the A annulus. Of course, because the pressure is so high, they cannot continue with the production. They have to stop the production. And it's become like urgent to address. So what they do, they decide to do the fiber optic sensing or distributed fiber optic sensing using the slick line, because they don't have a permanently install fiber optic here. And what they doing or to analyze this one is to make two different, right? One is that for investigation or diagnosis work like this, we always try to change one condition to another condition. On this one, what we do is that we record while the well shut in and the annulus shut in as a baseline, and later on we open up the annulus to let it flow, and we'll observe what happened there. So what we get is this one. So we have acoustic sensing, distributed acoustic sensing on the left, and the temperature sensing on the right. You see here, this one is when the well is being shut in, and this is when the annulus being open. So you start see some noise here, and many of a different feature here. So this one probably like contact moving up, and this is something here, and then something here, something here. So basically, many of feature like this one is related probably to the completion here. This one related to this one, I don't know what, right? Probably fluid level, and this one is an indication of flowing going up, right? And when we look at on the temperature side, what we see is like this. So when shut in, is nothing happening. When we open up the annulus, this one is like something fluid moving down, this is cooling effect. At the same time, heat or hot liquid moving up. So probably this is the fluid coming from the well. This is from the fluid on top of this one, because this one has when you bleed off this one is tend to have a fluid moving down here. So from this one, what they see is that this particular gas lift mandrel we initially put with the blank part was leaking. So what we do for this particular intervention or addressing the very simply just use the slick line, change the valve, put back, and flow the well, put back on the production. So this one is a case where you really need something to understand your well before you probably mobilize the rig or mobilize more heavy equipment. Just by simply running the divorce, you can address your problem even with a slick line. This is another one, a case where in some of the, I would say, try to be economic cheap well, you probably, when you have the reservoir, you did not cement the production casing all the way up to surface. What you do, or what they do normally just cement it up to above the production zone. So only this one, because they do not think anything particular or dangerous that they need to isolate. And what happened then, they have a pressure on their annulus. Of course, you do not have cement, so can be from anywhere, but they think that they suspect the cement here is not good. So the question is that really from the depth, or where else that can be the source of your pressure on the annulus? So they did run the fiber optic on straight line, go down, and then bleed off. And I think they also try to see more than just a leak. They want to see how the well behaving. After they bleed off, they shut in, they flow the well, produce the well, and see what things happen. So this is what they get here. When they bleed off the annulus, what they see is this one. So just below this one, actually there is a sand permeable zone that giving this anomaly temperature here when they bleed off this one. So something must be coming from here. And this one also confirmed by the response of the acoustic or the noise. So the conclusion is that the pressure here coming from this one. And this just gets some additional data when you want to see the well performance, nothing to do with the identification of the source. So with this one, what the client conclude is that what we need to do, they have to put the cement plug somewhere here. So it's not like straight line work, or probably it's not the coil hose work, but probably you need a rig to address this problem. So you will not mobilize equipment that is cheap if cannot solve the problem. But by understanding the problem with this well, then you can come up with something that exactly needed. You not just mobilize expensive, but actually you can address with a simple way, or another way, you probably need the more heavy equipment mobilization if you know the problem is this one. Now the other application for the fiber optic sensing is for well performance application. But before I talk about that one, I like to little bit go through the magic of temperature log, right? So my experience when dealing with the data, what normally I use as one of the important measurement is the temperature. Why? I will just go through how this thing gives you some good information. For example, we have a well where you have the production unit here. The spinner response will give you response like this from 0 to maximum, and the temperature depending on what type of fluid you are producing. If it's heating up like this, it can be oil or water. It's simple like this. What about if I'm producing gas? Example, if you have a gasket that going down to the liquid zone, you don't want to happen, but you suspect that may happen. The response is whenever you have gas, you will see the effect of cooling effect like this. So the spinner response is exactly the same, but the temperature response is different. Then one is a liquid produced zone, the other one is gas produced zone. What about if you think that you produce, or your geologist convince you that you have a gas or you have an oil zone, but when you produce it's full of water, right? That's one, the answer can come from the temperature too. What you see here, the spinner is exactly gives you the normal response, but the temperature responding differently. Where you see the deviation is not in the place where you want to produce, but somewhere below it. So it is a channeling. So information like that is very useful from the operator. And another one is for profile production. You can see a different profile like this, giving you information on which one is contributing, which one is not, how big is the contribution, and so on. And also this one, when you're dealing with the fifth zone, you think that you're producing okay, but why the production suddenly drop? You probably have one low pressure zone on top that you already squeeze, but halfway of the production it's breakdown and some of the liquid going into that zone. You can observe from the temperature response, or in other application you have the injection and then you want to observe where actually your loss of your drilling, for example, you want to know where actually the fluid goes. We can track back from the heating up of the zone which receive the fluid normally going very cold and then slowly going up. Now this fiber optic things sensing we can use for that part, for that. It's not answering all what you want to know, but sometimes just give enough data for you to know. So the way we do it, if we want to evaluate the profile or to see the contribution, we use this fiber optic measurement. We got the single line response. From this one, we go with the thermal model simulation, and then from there we get what we call matching the production profile. I'm not good on mathematics, but I just want to mention the principle that we use for this evaluation. Currently, there's so many models we can use, but the most common one used is the steady state with the assumption of this one, mass balance equation and energy balance equation. So basically, whatever you produce, mix, and then at the end has to be the same. So between low and high enthalpy, when you mix together, the total has to be remain the same. So that's where your temperature model come up, and then you get the what should be allocated for the rate at that particular zone in order the temperature match with your measurement. So this one is you cannot see very well, but the red one actually is underneath the green one. So the red one is the temperature we measure from the well, and the green one is the reconstruct of the temperature based on this contribution assumption. So when we manage to match the temperature to the actual measurement, we consider that the contribution is correct. So this is how we build this production profile using the temperature. This is another case. So this one is a little bit complicated. One thing that I would like to mention here, what we need to be aware of, right? In order for you to use temperature to generate the production profile, you need at least the pressure of the reservoir. Because this one at least is not like production profile we expect from the temperature. But we know this reservoir is low pressure and this one has high pressure. So what happened here is that because of a high pressure, different pressure drop, you tend to have more cooling effect here than here. And when you got here, you have less cooling effect, and at the same time you have compared to this one, provide high temperature. So what you see is not like cooling effect here, but more like heating effect here. So when we build the model, we put that one into our calculation, and when we manage to match this to the blue one is the reconstruct, the red one is where the actual measurement is, and this one give the result like this. So this is a few application of the fiber optic sensing on either for addressing the problem with the well integrity, or if we want to know the performance of your wells, identify whether you have something that you can improve or cure or plug off, things like that, using the temperature from the fiber optic sensing measurement. Just to summarize what I've been talking about, so the fiber optic sensing offers you with the information for you to optimize your operation in case like you want to address your well problem, or to optimize your well performance using the fiber optics information. And why this is become important today? Number one is that now you have opportunity to use fiber optic in many different ways. You can use on the college grouping, you can use on the E-line, you can use on the slick line, or also there is a disposable fiber optic. You drop the well and then you leave it there, wait for 6 months before you do the intervention, just to make sure the cable is not obstructing your production. Or like in the old days, if you rich enough to have the well to spend the money, you can put the fiber optic installed permanently. But that luxury information may not be available for you, but the problem you may have the same. So now you can use that one. Say for example, using the slick line, just convert to the fiber optic sensing. The beauty about this technology is that you turn the whole fiber optic as a sensor. Basically, you run the hole, you got all the measurement, you will not miss. And you can measure this in a second, instantaneously, from the top to the bottom, and you can repeat as many as you want, right? And then also the important one is that with the ability to handle big data, now you can use both the acoustic sensing and the temperature sensing at the same time to understand your well performance or your well problem. And more importantly is that now you have a dynamic picture of your well recorded with this one. So in the past, what we can do is we just record single line. Now you can record first time and see how the fluid level moving, or whether there is different changing on the contribution and so on. So this fiber optic sensing, because of the capability, is good to address for your well integrity or for your well performance, and in two ways. One, the information you can use right away, like in our case, to address the leak on the Gasman well, or as part of your information that you keep to understand better your reservoir or your well integrity. With this one, I conclude my presentation, and thank you for your attention.
Quiet. No drinking, no more drinking. Any question from the floor?
Thank you about it. But I studied the fiber optics a long time ago, and I did a lot of pressure temperature surveys in the time when you had that little line on a graphite piece of copper.
Yep.
With this, you say you run your fiber optic line all the way in the well, and you use your whole line. But for the temperature, what I still remember, you and what your pictures say, you got a sensor,
Yep.
right? So, and that sensor is the end point.
Okay.
Not?
No, but that just
No, so I'm trying to learn
Yeah.
here, yeah. So don't get me wrong, eh? Yeah. So you got your sensor at the bottom according to your thing, and then you got what? Couple of 1,000 feet of line,
Cable, yeah.
and then you're going to say, all right, what's your temperature?
Okay. Yep.
Okay, so my thing is, how do you do that?
Okay. Let me go back to the animation here. First, as I mentioned earlier on, the fiber optic sensor doesn't need electronic, doesn't need power. So the sensor is on the fiber.
Yeah.
Okay. And have you said that, right? Is it accurate? Maybe not.
Doesn't matter.
Yeah.
It senses.
Okay. Yep. And normally what we recommend to run in case of this non-permanent deployment, which is you straight line, or we have another sensor, which is one sensor at the bottom of the fiber optic to
Yeah, but that's a bottom thing, so your sensor, from that reflects the line.
No, the sensor is continuous along the whole length of the well.
No, that is the noise.
no, like this. Agree. No, when we pass one line like this, it reflected a light. When we pass another light, it reflected a light. So this is the one we convert to temperature.
Agreed. No, I agree.
Yeah.
Because it's reflecting the line.
Yeah.
So, from the company, your company bought long time ago, said, yeah, just wrap around some fiber optic around the pipe, and I've got an algorithm that'll tell you the mass balance that goes through it. 2008. Yeah. Yeah? And then
I don't know. Maybe I wasn't born yet. No, probably I was still a field engineer. I don't think about this anymore.
same here.
Yeah.
I was looking forward to say, all right, how's it working now?
Yeah.
Which algorithm you using now?
No, I mean, in terms of the technique is the same. The principle is exactly the same. We send pulse, right? So the way we send the pulse is depending on what the spatial resolution you expected, or vertical resolution, wide or narrow, right? And then there is a cost of playing around this one, right? And soon we send the pulse, bang, one pulse, right? You get a refracted light, which is representing the whole length of the fiber optic, and then we chop off.
From so your algorithm chops off.
Yeah.
Okay.
So we have every section of as expected as we expect, right? Of the depth or the length of the fiber optic individually by.
I know. I learned that the reflected part at the bottom determines your temperature, but that's at the bottom where that reflection is.
Yep.
So I did not know from that you can then determine the temperature, 1,000 feet above that because of that reflection. I don't know.
Yeah, okay.
You say you can.
Yeah. Yeah.
Is that true?
Yeah.
Okay. I learned something.
Okay.
Thank you.
Thank you.
You're welcome.
โอเคครับ
Thank you for your presentation. My name is Warapat from Chevron.
Thank you.
Several years ago, we have 3 wells with permanent fiber optic in the well, and it's very expensive. But what we gain is we want to know the real-time data. But what you present is that slick line included, and we need to rig up the slick line to measure every parameter what we want: temperature, pressure, and flow. And what is different compared to the tool that named production logging,
Okay.
MPLT?
Okay. If my background is a production log, what we call it funds, right? So I would prefer to have production log for the evaluation. Okay. Why? Because it has so many things. You have pressure, temperature, spinner, density, and then hold up, whatever you put there, right? And in many cases, it helps more detail of the evaluation. While from this fiber optic, what we get is only temperature and temperature and temperature, and sometimes we look at the noise, right? And is there any application? Yes, of course. There is application depending on what you're looking for. If you come to me, hey, Riko, I have a problem. What is my zone is producing water so much and so much oil? I say, don't use my fiber optic sensing. It doesn't work. You have to go with the PLT. But if Mr. Kasian told me that his well has a problem with intermittent problem, after 5 minutes I bleed off, just go to 0. I will not ask you to run, Mr. Kasian, to run the PLT. Even if you want to pay like 10 times more, I said, no, it's not your application. You need this tool. Why? Because I need something that can measure right away from top to bottom. And since you want to know about the leak, then this is exactly the temperature and the noise just enough to do the work. So, to answer your question, yes, there is application where this tool has a better way of succeed, and there is also PLT probably is the way you have to run. You cannot use this one as you, but like your case in a permanent installation of fiber optic, sometimes, especially if you're producing gas, sometimes it's good enough to understand your reservoir when, say, you start having problem with the water breakthrough. By comparing the measurement when your well is healthy versus when you start having issue with the water production, now you know which one you have to close your, say, your sliding sleeve and so on. Okay.
Maybe I check my understanding. Your two fiber optic you can run along the well and measure every reservoir at the same time because it's fiber optic. But MPLT you need to measure every sand at a single point and pull it up.
Yeah.
So in the very dynamic well, the well condition might change very fast. So MPLT may be not fit for that purpose.
That's correct. That's
But
correct.
fiber optic maybe can answer
Yeah.
the problem.
Yeah, I agree with you. Thank you.
Thank you.
With the luxury of time, can I have one more question, please? Last question from the back. Anyone? Counting 1, 2, 3. So, okay. That's it for tonight. Thank you very much, Pak Riko.
Thank you, brother.
Terima kasih banyak.
Actually, I'm quite relieved because before the presentation, somebody will ask a difficult question, but I think you decided not to ask, so it's good.
Okay.
Okay, thank you.
And this is, please, having Kun Ronald on the floor to present token of appreciation. Photo ไหมเฮ้ยเปลี่ยนสไลด์ก่อนอ๋อพี่ต้องเปลี่ยน
Thank you very much. A token of appreciation. Take it home. Is this some protection? Oh, yeah. More. All right. Thank you very much. Applause for Riko.
All right, let's continue with the rest. For the upcoming meeting in August, 18th of August, we have the SPE Mali technical meeting, the usual one, on the topic how making a shift in production mindset can transform production result by Kun Kelon Diaz, Global Production Solution Director from Baker Hughes. And of course, last but not least, on Wednesday is special event. That's why it's on Wednesday. In October, we're gonna have SPE Thailand season opening, and together with the SPE Thailand EMP Award presentation on 2021 and 2020 announcement. So we're gonna have a talk from Kun Montri, CEO from PTTEP, on the topic the next chapter of Thailand Upstream. And in the same event, we will have announcement of the winner of the ENP Award project as well. So please stay tuned for that. In August, we have upcoming event, IADC SPE Asia Pacific Drilling Technology Conference, an exhibition in Bangkok. So you can check out the website and join this event as well. And of course, the big event in 2023, IPTC, International Petroleum Technology Conference, hosted by PTTEP in Bangkok, 1st to 3rd of March 2023. There are many upcoming conference and also workshop in Asia Pacific region. You can also check out the website here. And I think that the upcoming one will be in KL and also in Bangkok as well. And I understood that you all know how to reach us, but again, just to remind that you can reach out on several channels. We have website, very traditional one, thaispe.org. If you are a bit younger, you can join our Facebook page or our LinkedIn group. And for the Generation Alpha, you can join the Line official, the one on the bottom right, or you can pick up your phone and take photo on the QR code, or ask any of our board members to show you how to do it. On the Line official, you can also book the meeting, or join check out our event as well. Okay, without further ado, may I have Pak Riko? Pak Pak Riko, lucky draw Pak. Two. We have very nice. Is that Mercedes Benz? Oh.
I need to take this one. just
แนทเอาของขวัญมาดิ
Please hope. No, it's bad, right? How many?
two
I will take 3 and you decide 1 to drop, okay? So you have a chance.
3 1 to drop.
Okay, 2 to drop.
Oh.
I will ask the ladies here, which one?
You just want to make it complicated.
Which one? Okay, I will tell later.
So the one that you fall down is not winning or winning?
Oh, this one not winning. Anybody want to take the chance? This one? Middle?
I'll take the right. Take that one.
Okay, because you have questions and I
don't.
I give you the hot.
He didn't give you an answer.
I did. Okay, this 2 is the winner. I don't like, but I have to.
Don't tell me Expro.
From my Jew. Who's my Jew?
From who?
Which company?
Start with J. Jasmine.
Oh, Jasmine. All right. Congratulations.
My paper bag. Thank you very much.
I will take picture because I like to be taken picture.
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 Thank you very much.
Seem very suspicious.
Another one there.
Oh, another one. Okay.
Thank you. Thank you very much. Sign contracts.
I was
Next one in line.
I was told that PTTEP is the one who sponsors most, right?
No, they don't. They don't.
That's the wrong information from me.
No, that's wrong information.
They should sponsor more.
So the next winner is Pata from PTTEP.
Okay. Congratulations ครับ อ้าว
Bobby!
She just left. Oh, OB. Okay.
No, which one? The winner. Left, right. Left, right.
Left one.
You too smart. We come back, right?
Oh, and it is.
Mr. Kada consultant is my mechanic.
All right, congratulations.
We always say that Rajaki never gone away. Congratulations.
เชิญหน้าม้าหน่อยดิ
I will not leave this one, otherwise he disappoint me. This one will
Okay, thank you, Riko. Terima kasih banyak. So if you think that our drink for tonight is not enough, you can continue the journey at Rendawas on the ground floor. We have a 2-for-1 promotion. Just mention that you are from SPE Thailand. And of course, another loud applause for our generous sponsor. That's it. That's my last slide. Thank you very much. แล้วเจอกันใหม่ครับ Sampai jumpa lagi.